Welcome everyone to this week's SQL training. This week we're going to be covering top function in SQL queries, ranking, Ntile, and analytic functions. This is brought to you by Emergency Reporting, and I'm Steve Stedman, and Aaron Bouma will be helping me with the presentation. For those joining us remotely, if you have any questions via Google on-air broadcast, we'll address those at the end of the training. And just want to say welcome to everyone, whether you're joining us from Michigan or Florida or somewhere across the world. We've got some good stuff to cover today. Training is provided by Emergency Reporting, like I said. This is a class that was done, or it's intended originally as internal, but we decided to share it with everyone. And again, my name is Steve Stedman, and Aaron Bouma will also be presenting. This week, what we're going to cover, pretty big list of things here, but we'll get through it in the time we have. How to use the top function. And this is one of those that Aaron will be presenting, and although I've used the top function many times, I learned a few things from what he's put together. Rank and dense rank, as well as using row number, the Ntile function, overclause enhancements. So previously we did cover a few things on the overclause. We'll go into a little bit more depth there. We'll take a look at some of the analytic functions, which include the lag and lead, first value and last value, followed by percent rank, percent discrete, percent continuous, and cumulative distribution. So at this point, I'll hand it over to Aaron to cover the first part of the presentation.
All right. First, we're going to do some demos on the top function and what we can do with it, how it handles duplicates, and with top percent, and how to use it as a variable. And then we'll cover rank and dense rank and the differences between the two, and then we will cover row number at the end. All right, so select top n. N can be a variable. We're going to cover how it can how it deals with duplicates. You know, does it continue on with selecting more rows? If you want 5, will it return 7 or will it return 5? And then what the syntax is for doing the top 10 or 50%. All right, so what we're going to do first is set up our data. And the data for today is just a simple inventory database with items and SKUs and descriptions, quantity, unit cost, and unit retail. So right now the top query in the results pane is a select top 3. It does not have an order by. The second query does have an order by on it, and you can see that in the second query it orders by the quantity on hand descending, as we type here. However, the first query, since there was no order by included, there's no guarantee on what it's going to order by when the results are returned. So it's always a good idea to have order by on there, because depending on, it changes how the table's set up. Is a deciding factor on how it returns, but there's no real guarantee on what it's going to order by when you do a select top 3 without an order by. So now we will go on to how you can have it do a select top n rows if you want to have a variable number of rows returned. When you do that, you can have it as a variable, but when you do that, you need to include parentheses around it, and you'll get a warning message if you don't, so it won't let you do it. But just a little tip there. So now, how does it handle duplicates? So we can see in the full data set that for sleeping bags, we have 3 sleeping bags, and they all have the same unit cost. So if I run a select top 2 of a unit cost and item SKU for sleeping bags, we get 2 rows. When we include the with ties clause in the second result set down here, we can see that even though we said select top 2, we said with ties, and then the next column is unit cost. Any rows that match that second row, so if it was top 3, it'd be any rows that match the third row. So any rows that match, it will continue to return the rows. So if we had 10 more rows in the sleeping bag category with the unit cost of $5.75, it would return 10 more rows. Top n percent. Select the data set again. So we can see we have 7 rows here. So select top 0%. No, won't return anything. Select top 10%, 1 row, 20%, 2 rows. But sometimes you don't want to hard code your percentage, so you can have this as a variable as well. And it can be any number between 0 and 100 inclusive. So it can also be a decimal. So 10%. Now, if we want to return 15.2%, in a larger data set, that might return, 15, a more exact row count. But we only have 7 rows in our data set, so it returns 2 rows.
Rounding up the percentage. So it's not 10%, it returned 1, but
yeah,
only 7. So it would.
Yeah,
down,
it does round. But you can go as detailed as you want on the percentage-wise. You can have a float, an int, decimal.
And although the small table is really good for doing the demo, generally you're going to be using top one in bigger tables. So
yeah,
the precision on that rounding is going to be a lot more accurate when you're dividing it across 10,000 rows than 7.
Yeah. Okay, so those are all select statements. So what about delete statements? Can we delete a top 3? And you can see the first result set is the delete. This is wrapped in a begin trend and rollback trend, so we don't lose any data for the remainder of the training session. But so the first select is we'll return all the rows, so 7 rows, and then we do our delete top 3, and then we do a select again, and we can see that now there's only 4 rows. But since I didn't have an order by on here, it's a crapshoot on what rows it's going to delete. So that's kind of a dangerous statement to have in there. And then one thing to know about the delete when you do a top 3 with an order by on it is it does a delete top statement similar to a with ties. So if the third row in whatever we have it ordering by matches more rows, or that third row value matches more rows, the with ties statement will delete all those rows as well. So you could end up deleting more than 3 rows when you do delete top 3 order by a column that has many duplicates in it. So can we do an update top 3? I have 10 there, old comment. So ignore the squiggly line there. No, we can't do an update on top 3. So how do we, there has to be a way to do it. So how can we do it? Once again, I wrap my whole update in the begin trend, rollback trend. And first we will select the item SKU and quantity on hand, order by item SKU descending to show the before, and we'll do it again after to show the before and after. But in the update statement, to update the top 3, so the goal is to reduce the quantity on hand for the top 3 highest values. So we select top 3 in inventory IDs. So select top 3 IDs from the table, ordering this subquery how we want to get the top 3 values, and then we have the select statement, or sorry, the update statement, which will perform the update where the ID matches the ID from our subselect. So let me make this a little bit bigger here. So here's our result, or our initial data layout. We see we have a 35, a 13, a 5, and a 5, and a 5. And then we ran the select after the update, which returned a 30, an 8. Oh, and it only grabbed one of the 5s and set that to 0. So what about an update statement with ties in there? So you put a with ties in the subquery. Here's the original data, 35, 13, 5, 5, and a 5. Now we have 30, the 8, and it caught all those 5s because that was the third value in the order by. And the with ties statement grabbed all of them, and the update statement reduced the quantity by 5.
So what was 35.5?
So the question was, how is 35.5?
Because it updated 35 to 30.
Well, what it does is it grabs the top 3 inventory IDs. So the ID is, it's not in the output here, but it would grab the 35 row because it's ordering this subquery by the quantity on hand descending. So this has the highest quantity on hand descending, quantity on hand out of all the rows. And then the second row of the subquery would be 13. And then the third value in this with ties, because it includes all duplicates, are these 3 rows right here, this 5, this 5, this 5. So it reduced that 35 to 30, this 13 here to 8, and all these 5s
Okay.
down to 0s.
So it counts all 3 5s as one
Yep.
row.
Because it had the with ties. In the previous example, it did not have the with ties, so it only grabbed one of those 5s and reduced it to 0. Okay. Now we're going to rank, dense rank, and row number. So these are values assigned to the output row number, not row number function. And it is a way to kind of organize your result set. There's rank and dense rank, and those will, when you declare them, you set an order by after them, so you can tell how to rank those results. So you want to rank by, say, your second column. You'd say, rank over that second column, order by that second column, ascending or descending, and it'll put an ordered rank value associated with that. Rank and dense rank have a difference where if there's duplicates involved, rank will repeat that row number. So say your second through fourth rows contain the same value, but your fifth row is different. Rank will return the rank of 1 for the first row, 2 for the next 3 rows, and then 5 for that fifth row. So it skips that third and fourth value.
Like golf. Golfing.
Yeah, sports rankings do have that. Dense rank will continue the ranking sequence. So your fifth row would have a rank of 3 versus a rank of 5.
So if you're golfing, Cody, you need to use one of those, and if you're doing other sports, you might need a different one.
Yeah, maybe. I don't know.
So if your results are all unique, rank and dense rank will return the same values. The row number function just ignores all duplicates and just returns a row number for every single row, a unique row number. So now we will do some demos on that. So the first select is a rank. And the second select is a dense rank. Then we can see that, so we'll cover the first one, and that's rank. 1, this is unique, so it's rank 1. This is unique, so this is rank 2. This is the next unique, rank 3. Oh, and the first duplicate's encountered, so this one repeats the rank 3. But on row 5, it doesn't match the row 4, so it tagged on the next rank. But since it's rank and not dense rank, it skipped over rank 4 and just starts with the row number. And 6 continues on. If there was an 8th row with a different skew and retail value, it would say 8. The rank value would be 8. This next result set is dense rank. And same thing. First row is unique, second row is unique, third and fourth rows are the same, so we get 3. But the 5th row is different, and it continues on with the sequence. It doesn't have a 5. It's okay, this is the rank number 4, and then 5, 5. Continues on. If there's an 8th row with a different skew and number, the dense rank number would be 6. So how can we get the items with the lowest unit retail prices? So not just the items. We want to first get the lowest retail, 5 lowest retail prices, and then any items associated with that. So one thing we might try right away is just plopping that aggregate or the windowed function into the where clause, and that doesn't, you can't do that. That doesn't work. What we do is we create a subquery where we first select, we assign a rank based on the retail price. You can run that first just to show you. So we can see here that using the rank function, it tags on a retail rank of 1, 2, 3, 3, and then 5, because this is the rank, and it skips if there's a duplicate encountered. So then we can filter on that, and here's the result set of the lowest 5 items. So when we use a dense rank, it returns a different result set. And that's because we can see that 19 is duplicated, and 99 or $100 is duplicated as well. So we get 1 distinct retail value, 2, 3, 4, 5. So in this question of getting the items with the 5 lowest unit retail values, you'd want to use dense rank because some of your items have duplicate values in there.
If no was in that column, where would it be? It would be the least? Or,
If null,
yeah, no.
it wouldn't filter on that.
Okay.
So now I just run a query just to throw all of them together, and we can see how I added row number onto this one, so we can see how it is included. We first is item skew, unit retail, and then we rank on unit retail ascending, dense rank on unit retail ascending, and our row number on unit retail ascending. We can see that, just kind of a recap, just the rank function itself skips rank values when duplicates are encountered, because it skips to 5 here after the 4th row is a duplicate. Dense rank does not skip sequential values after duplicates are encountered. Just continues on with the next sequence number. And row number just doesn't care about duplicates. It just keeps going. So it's a handy way to say you want to grab the top one out of duplicate rows. You can have that in a sub-select and group them together and just grab the top one out of that group to get a top one out of multiple groups contained in one result set. And that is it for my part. I go on to Steve, as Ntile Analytic Functions.
Thanks, Aaron. So the one thing I wanted to point out, if those people are joining us remotely and you want to get access to the slides or the queries, or anyone here as well, they're available on my website, stevestedman.com. There's a post there you can download them for now. And then everyone internal here at Emergency Reporting, they'll be available in the usual location. So I'm going to take a look at the Ntile and Analytic Functions. So part 2, we'll take a look at Ntile, which is sort of a way of breaking groups of result sets into kind of like a percentile, or a way of breaking it into different bins or different categories. So I'll go into detail there. We'll take a look at more detail on the over clause and some new enhancements that we haven't covered before, around like being able to look at the previous rows or following rows, or rows outside of what you're normally looking at or what we looked at before. We'll look at lag and lead, which is a way of saying I want to look at the row in the result set and the row just before that, or the row just after that, which is really interesting because prior to lag and lead, that's been a very difficult thing to try and do with some nasty joins and whatnot. We'll take a look at first value and last value, and that's in regard to the windowing functions. And then we'll jump into percent rank, which is similar to what Aaron just covered on rank, but we'll take a look at how that differs. And then percentile discrete and percentile continuous. And then we'll take a look at the cumulative distribution. And with that, we'll run some random number generation things to go and like simulate the roll of a dice or random numbers and test based off of this whether they're really random or not. So Ntile, this is a way to break result sets into different chunks or different subgroups. And think of it as if you had a group and you established the median, everything below the median would be one group, everything above the median would be another group. And it would be 2 evenly sized groups, plus or minus 1, depending on whether there's an odd number in the groups or not. So it's as close to even as possible given the numbers we've got. Now, a quartile is similar to that, but you take the group and split it into 4 evenly sized groups. So if you're in class and you're in the bottom quartile, you're probably not doing very well. But if you're in the top quartile, you're probably doing pretty good. Decile, and this is one I hadn't really even used before, but it's a way to split the group into 10 evenly sized groups. So if you've got 1,000 people in the room and everyone, let's say, took a test and had a score on that test, and you split it into decile, the people in the 10th decile would be the 10 people with the highest score, independent of what those scores were. And the people in the first decile would be the 10 people with the worst scores out of that entire data set. And then there's percentile, and you always hear this in school, or when you have kids and you go to the doctor when they're young, they always say your kid's in the whatever percentile weight group and whatever percentile height group and all that. It's basically similar to decile, but it's just taking the entire group or a set of people and splitting them into 100 sized groups. So if there's 100 people in the room and you were in the 97th percentile for height, let's say, that means there's 3 people in the room who are taller than you, 96 people in the room who are shorter than you at that point. And then there's Ntile, which is what this function is, which is similar to all of these, but what we're doing is we're going to split the group into n evenly sized groups. It's not 10, it's not 4, it's not 100, it's whatever n is that you decide to do. So let's take a look at the code on using the Ntile function. So we're using the same query training database, but I'm going to drop it and recreate it and create a table here called revenue. And then in that table, I'm going to add a number of values. And you can see the 3 columns here. we're putting in a department ID, a revenue amount, so think of this as dollars, although it's just an integer, and then a year. So this would show for Department 1, in 1998, they made $10,030. Department 2 in that same year made $20,000, and Department 3 made in that same year $40,000, and then it's down through the list through a total of 1998 to 2012. So we'll fill this table up with some data so we can play with it. And keep in mind there's 45 total rows there. Now let's take a look at what we've got in there, just a quick check. So 45 rows come back, page down the bottom, and they're just in whatever order they happen to be exist in the table, with a department ID, a revenue amount, and a year. So it might be typical stuff that someone's doing for some kind of financial forecasting. So if we want to rank all of the revenue amounts on a scale of 1 to 10, so we can figure out, okay, what was the best year, the top 10, or sorry, what was, let's say, the top 10% of revenue years for any department, or what was the worst, or what was the middle on that. We can run this, and this new, I didn't put an alias on it, so it doesn't have a name here, but it shows that if we look at department ID of 2, revenue of 20,000 for the year 1998, this is in the second decile, because we're looking at a total of 10. So it's in that 10 to 20% category of revenue. So there are 80% of the revenue months are better than this, and 10% of them are worse than this bin that we're in here. The next one is the fourth bin, and that shows that 30% are less than this bin. And then there you can see down here, there's other ones that are kind of in that same range that are in the fourth bin. As we scroll through here, we can see the top 10 is the very best years in the entire data set here, which were $90,000 for Department 1 and Department 3 in 2002 and 2003. So and then there's 2 other years that are down here that are good years for 2012 for $90,000 as well. So it's a way to assign those different bins or different categories of the results that you're looking at there. Now what I'm going to do, the only difference here is I've changed this to 100 to effectively calculate a percentile then. I've given it a name, percentile, and I'm ordering by year. So now when we run this, should be calculating percentile. And as we look through, though, the highest number in this entire list is 45. So even though I asked for an Ntile of 100, which should be similar to a percentile, it only does that over the number of elements in the table. So there's only 45 elements in the table. So it's really giving me an Ntile of 45 because that's how many are in the table. So keep in mind that's one way that you might get a little bit confused on your result set. So if you're working with bigger data sets where the number of rows is greater than the Ntile parameter that you're giving it here, it's all going to work out good. But for anything less, it might throw off your result sets. So here's an example where I'm selecting the same things. I'm looking at the Ntile of 20. And again, I didn't point out, we're using the over clause. So this is the Ntile of 20 ordered by revenue. So we're ordering by the best revenue of Ntile 20. And then we're going to order, not by the year, but order by the results that we've set here on the alias. So when we run this, we can see now the Ntile, so it's in a sorted order where the absolute best ones in the 20th tile down here are in based, and keep in mind, we're doing it off of revenue, which I'm confused as to.
Because it's descending.
Mm-hmm.
Oh, you're right, because I did descending. Thanks, Cody. I was looking at it backwards. So if I wanted it in ascending, I can change that. And the worst revenue year of all, and the next 2 worst ones are in this first tile. But you notice in the second Ntile 20 here, there are numbers that match the first one. So even though, I mean, what it does is it splits it into so many chunks and puts the most items into that chunk to evenly balance it out. And if there's too many in that chunk, they'll get bumped up into the next tile there as well. And as we scroll down, you can see the 2 very best years are in the 20th Ntile, but the next two that tie it are also in the 19th Ntile. So it splits it all out evenly and puts as many in each group as it possibly can there. So what if we were to change this, instead of ordering by revenue, if we said order by year? Well, at this point, it's simply going to put them in year order rather than revenue order. Not entirely useful, but it goes to show that if you don't have the right thing in your order by clause here on the Ntile, you may not get the results you want. All right, so let's take a look at using multiple Ntiles. So here we're going to, using the same table, give me an Ntile of 10, an Ntile of 20. Whoops, it's only right. An Ntile of 20 and an Ntile of 4. So the 4 is the quartile, like we talked about. The Ntile of 10 is the decile, and then the Ntile of 20 is just, I don't know if there's a name for that or not. But we're going to get the entire result set, and we're going to order it by the Ntile of 20. Now, because all of these are Ntiling over the same item, they should show up all in the same sorted order. So we can see here Ntile of 10. These are the top 10% of the very best years. Very best revenues. These three that are shown here are the Ntile. Let me expand this a little bit. Ntile of 10, these are the top 10%. These here are the top 5% because we're dividing it by 20. And then the quartile includes quite a few more, as you can see there. Now, what if we were to change this like we did earlier and say we want to order by year rather than revenue? All of our windowing functions where we're using the over clause with the order by here don't have to be on the same items. So if we run that, our Ntile 20 is going to be over a different data set than our Ntile of 10 is. So at this point, this Ntile of 10 column is putting it in the top one Ntile of 10 for years, where these three are the top one Ntile of 20 for revenue. Does that make sense there? All right, so let's jump back to the PowerPoint. Next, we're going to take a look at the over clause. So we've used the basic over clause there, where we were using it to look at a different window of data, and we were ordering by different columns. And prior to SQL Server 2012, that was it. That was about all you could do with the over clause. But in 2012 and 2014 and beyond, there's been some enhancements here. So there was actually the one I forgot to mention that was there previously was the partition by, which we've looked at before. Partition by was there in 2012 as well. And that's a way to say take the group and or take a column and group or partition by that column rather than the normal thing that's being used in our group by clause. But what's been added now to the over clause is the ability to say, look at rows preceding, following, or unbounded, which means to, instead of the windowing to be just grouping or partitioning over a specific chunk, it's going to say, give me the current row inside of that group or chunk and look at n number of rows preceding. You might say, give me 2 preceding or 3 preceding. So if you wanted to look at revenue for the trailing 3 years or something like that, you could calculate it out where you're looking at the current row, the previous row, and one before that, or 1 or 2 before that, depending on how you're doing your math there, to get those kind of values. Or you could be looking at future data set there as well. And the unbounded is a way of saying, don't look at just a certain number of them, go all the way back to the beginning of the result set. And range is almost identical to this, but like we saw in the top function, there's the with ties. So range is like saying rows with ties. Range will include all of the ties in that result, not just the number of rows. So for example here, if we look at this data set, where we're looking at years, and there happens to be 2 items for year 2005, if our windowing function is over year, and we're calculating the rows cumulative, it's going to, for instance, to add these up, there's nothing before this, so the revenue is 10,300, the cumulative is 10,300. Then the revenue is 10,000, the cumulative is the 10,300 plus the 10,000, which gives us 20,300, plus the 20,000 for the next one is 40,000, plus another 10,000 gives us 50,000 when we're looking at the cumulative total going down there with rows. But when we're looking at range, notice these two right here are exactly the same because it's including the fact that these 2 years are tied here, and it's like saying, give me the rows with ties. So in that, we'll jump into the query here in just a second. Keep in mind that when we're looking at preceding, following, or unbounded, we have the concept of rows versus range, and range is like rows with ties. Preceding tells it to look at the rows before the current one. Following says to look at so many rows after the current one. Unbounded is telling your result set to, or telling that windowing function to look at all of them until the end of that partition, or to the beginning of the partition, depending on whether you're going preceding or following. And current row is a way of saying just reference the current row that we're at now. So for instance, the way this all goes together is inside of your select statement, you would have a aggregate function like sum of revenue over, and then partition by department ID, meaning we're grouping this windowing function on departments. We're going to order by year, because we're looking at revenue year over year. And then we're going to only look at this window is the rows between 3 preceding and the current row as previous 3. And maybe the better name for that would have been current and previous 3, because with this, you're going to get a total of 4 rows that are being calculated in that windowing function. Here's another example. Sum of revenue, same thing on the partition and the order by, but here we're looking at between 1 row preceding and 1 row following. So it's going to give us a sum of revenue for this year, last year, and next year, where this year is referring to the current row there. All right, on to the demo. So quick review, like we mentioned on the over clause, this was all available prior to SQL Server 2012, and we've hit on some of this before. So in this case, we're looking at the average revenue partitioned by a department. So the average revenue for each department and the sum of the revenue for each department. So, and we're going to order by the department ID and year. So when we run that, we can see that the average revenue here, which let me make this a little bit taller, the average revenue here of $35,355 is for all items in department ID of 1. And then the average is for all those in department ID of 2 is $41,400, and the total revenue is $530,330 here. So that's just the basic partition by where we're partitioning by the department ID, and it's taking that aggregate function and applying it to all the rows that have the same department ID. So next, and I guess I should point out here, there's a number of items over the last several years that I've blogged about or talked about in different blog entries. So whenever there's one of them in the sample code that I knew I had somewhere in my blog, I put a link in here. So as you're looking at the sample code, if you want more detail around it, just copy that function off or that URL off your browser, and you can go see more information on that specific area. All right, so now what we're going to look at here is looking at just the year, department, and revenue. We're going to look at the sum of the revenue, very similar to what we did up here. We're going to partition by department ID, very similar to what we did right here. However, we're going to order by the year, and when we're looking at the sum, we're going to only look at the rows, the current row, and the 3 before it. So this is exactly the query we looked at in the slide, in the PowerPoint slide. We're going to grab it from the revenue table, and then the results will be ordered by department ID and year. So when we run this, we look at the revenue. The first year revenue is $10,030. For the current year and all previous, it's still $10,030 because there are no previous years. The next one is $20,000 for the revenue, and the previous 3 is the current one and the 3 before it. but there's only 2, so that adds up to about 30,000 there. Next one is 40,000, so the total is the total of all 3 of those there. The next one is around 100,000, which is the total of all of those being the current row and the 3 before it. Next, it's 180,000, which is the total of the current one and the 4 rows before it, and it's ignoring the first one because that's outside of what we've specified for the windowing function for this. And you can see as it goes all the way down the list, when we hit department 2, you can see it starts again, 20,000. There's none previous to that in the current windowed group, so it's only 20,000. The 80,000 is just those 2 totaled, and the 120,000 is those 3, 150 is those 4, and so on.
So why was that outside the windowing group, the first one? What?
So notice right here between these 2, the department ID changes. And if we go back to the query, we're partitioning by department ID. So each department ID is treated almost as a completely different result set in how the sum is being calculated here. And that's the partitioning. It's a way of...
That had the same department ID. It had 1.
So right here it breaks between department ID 1 and 2. Which one are you talking about? The top?
The first one. You said that wasn't included in the one that after 90,000. That's why it's 180,000.
Oh yeah, right. Okay, I see what you're saying. So let me scroll this down so we can show both of the query. So here I'm saying look at the rows between the current row and 3 before the current row.
So 4 rows.
So if we go here, this 80,000, for instance, is 80,300 is the current row plus 3 before it.
Okay.
If we look here at the 140,000, it's the total of the current row plus the 3 before it. So it's saying just look at the current row and then add all of those up on the 3 preceding rows. If we change this 3 here to a 4, it would look at not the 3 before it, but the 4 before it.
Is there a way to dynamically do that so you don't get miscalculations like that? Like kind of the departments?
What do you mean miscalculations?
Well, I mean, it seems kind of like static, you know, when you're doing that. So if you wanted for the department ID.
Oh, you could break it out and filter and say in here where department ID equals 1, for instance.
Okay.
And then that breaks it down. Oops, I typed it wrong.
Yeah.
Rule is never actually typed during demos. Always have it prepared. But there we go. So now you can see it's just for a single department.
Okay.
And then that gives you what you're looking for. But depending on what you're really trying to do, one way might be awesome. The other way might be the way to do it. So, all right. So now if we take a look at this next one, it's pretty much the same as the previous query. The only thing we changed was we're going to look at 5 rows preceding and 2 rows preceding. So this is kind of weird. We're going from 5 before to 2 before. Kind of a weird way of doing it, but it's showing how it actually works here. So put that up top there. We run that. There is nothing 5 to 3 rows before this, so it comes out as null. There is nothing 5 to 3 before that, so it comes out as null. 5 to 3 before this, or sorry, 2. 5 to 2 before this, go 1, 2 is the 10,030, so that's this number right here. 5 to 2 before this is these 2, which should be 30,030. So you're able to do calculations in a given row based off of data in other rows, which is just super cool. It really is. Having to do this without these features in the windowing functions and the over clause here, previously you'd have to do like joins of multiple queries against the same table, joining them all up, and it's just incredibly painful. So this allows you to do some really interesting running tallies over time. That otherwise would be very difficult to do.
You could use isNull if you wanted to get zeros in there.
Yes, absolutely. You could use isNull. Sum of revenue right here, you could say isNull. I think I have to break it all the way out here. Set it to 0 if it is null. There you go. You can get set to 0 that way. Yep. So now let's look at a 3-year trailing average. Previously, we were looking at sums, but oftentimes when you're analyzing a business or revenue, you have different spikes in different years and things. So a way to determine how you're really growing is to look at a trailing average. Defect velocity, is that the one that you guys use trailing average over?
I don't think it's a trailing average.
So that's just all-time average.
But like a velocity.
Yeah, you use trailing average there. So if we're looking at here an average revenue, still we're partitioning by department ID and ordering by year, and we're going to look at 2 before the current row and the current row, which will give us a total of a 3-year trailing. So when we run this, scroll it up so we can see the query, the average over the previous 3 years for the first one, well, there are no previous years, so it's just the current one. This one, there's only 1 year before it, so that's the average of these two, which is about 15,000. Then it averages these 3 out, which gives us 23,000. Then it averages those 3 out, which gives us 30,000, and we're able to get that average 3-year trailing result there. Okay, now that's all been, so far at this point, we've been looking at the current row to some rows before it. But what if we want to look at rows after it? Like instead of the trailing 3, we want to look at the next 3 years. So this would technically be, let me just change this to a 2 because I'm going to look at the current row and 2 more, which will give us a total of 3. So when we run this one, it's between the current row and 2 more after that. And one thing I want to point out while we're here, I just remembered too, is this rows here. It doesn't matter if you put row or rows, but because sometimes you're only asking for a single row and sometimes you're asking for multiple rows, SQL Server has made it so that you can be, appropriate on how you're wording it, because you don't want to say, give me rows of just the current row. So rows with or without an S is completely identical. What? Oh, hold on, that changed. Maybe that was a change in 2000. All right, take that back. I was wrong. I thought in 2012. All right, so it needs the S on it, apparently. Maybe I was thinking of something else. So let's take a look at this one now. Here we're going to look at the current row and 2 following. So this plus these 3 totals up to 70,000. This one plus those 2 following totals up to 90,000. This one plus the next 2 is 160,000. And you're able to use the windowing functions to look at rows that haven't yet been returned in the result set. So looking forward. And you can use a combination of preceding and following. So here I want to look at the current row, 1 before and 1 after. So when we run this, the 30,000, that's just these 2. Scroll this up here. That's just those 2 sums. The 70,000 is all 3 of these sums. And notice when we get to our partitioning breakdown here between Department 1 and Department 2, this 90,000 is just these 2 values, and this 80,000 is those values because we're switching into a different partition bracket there.
Sounds like we can predict the future.
I know. This is how you predict the future of SQL Server.
Yes.
Can you do that with alphabetical, like strings? Does that work?
Yeah, you can do it. Yeah, with any of the data types in SQL Server that go into the order by, which is pretty much everything. I don't know, var binary might not work appropriately. I don't know, I haven't tried that. But yeah, you would just say your order by and order by the varchar value here instead of ordering by an integer value. It works just fine.
So when you're using preceding or following, you have to kind of consider null if you're using both preceding or both following. But if you're using like preceding and following or current row, then it's kind of impossible to get null.
Right. So anytime you're using the current row,
You're going to get,
as long as there's something in that in that column. Yeah.
yeah.
If the column allowed nulls, it could throw it off that way too.
Okay.
Yeah. And it might be that in certain cases you want to put the is null around the revenue rather than around the total if there were no values allowed in that set. Oh, I didn't repeat the question. So the question was around using accounting for nulls, and as long as every row in your result set actually has a number in there, you don't have to worry about null as long as you're including the current row. But if you're doing following only or preceding only, there's a chance that the row could come up null, and that's true. All right, so now we've changed it here. Instead of saying between, we've changed it to unbounded preceding, which means for this partition, which is our department ID, let's, in the calculation here of revenue, let's include all of the preceding rows unbounded. That means all the way back to the very beginning of the partition, and include that in the min calculation here. So let's take a look at what that does. So it starts out from the first one, there's nothing preceding, so it's only this value, and the minimum revenue is 10,030. Then we look at this one is considering this row and all preceding, and it's still 1030 or 10,030 until we get down to right here. So here, all of those, the minimum is still 1030, but when we hit this one, the minimum of all of those is now 10,000, and we see it change at this point, and that stays at 10,000 all the way to the end of our window, our partition by department ID. And notice as soon as we flip through to department ID of 2, that calculation starts over fresh. And it keeps going 20,000, 20,000, all the way down to here, where the new number is 10,000. And then we hit the end of our department ID here between 2 and 3, you can see it starts over again as well. So here we've got, I've just copied this line here, and I'm looking at the minimum revenue and the sum of the revenue, unbounded preceding, just taking a look at using it in 2 different columns. And here's the minimum revenue, and here's the total revenue so far. So you'll see the number keeps getting bigger and bigger and bigger until you hit the end of the partition, and then it starts over at a new value on that next partition. So here, I'm looking at the minimal revenue, same partition, same order by, but we're looking between the current row and unbounded following, which technically is the same as just saying unbounded following, because the current row is included in unbounded following, but I wanted to show how it could be used either way. So when we run that, now the minimum revenue, this minimum revenue is based off of all of these numbers, looking at the minimum value. This minimal revenue is based off of all of these numbers. As you see, we go through it, it's all the way down through the rest of the partition. So you can see here, after we pass that 1,000, that partition no longer has a number smaller than 1,000, so 10,000 becomes the minimum in that partition. All right, now we're going to take a look at range, because we talked about how rows is a fixed number of rows, but range is kind of like using with ties, meaning give me, if this, I'm saying unbounded preceding, we're going to look at rows unbounded preceding and range unbounded preceding. There should be no difference because we're not specifying any given number there. We're just saying look at all of them independent, where the year is between 2003 and 2008. So let's run this. See, these 2 columns are going to be exactly the same. You can see going through there. Rows and range, in that case, come out exactly the same. But let's put a duplicate value in. So let's say, due to a reorg or something, that department 1, 2, and 3 had 2 different revenue numbers for 2005. Maybe they changed how the fiscal year is accounted for or something like that. So we add some duplicate values. We run the same query as before. And what we're looking at is order by year, all of the rows preceding. And as we go through here, those are identical, those are identical, those are not. Because what it's saying is to calculate this number with rows based off of the year sort, include all of these values. And then here, based off the year sort, include all of those values with rows. But on range, it treats ties as though they're the same thing. So here, because 2005 ties, the range cumulative calculates out including 2005. So it's very similar to the with ties that we looked at earlier. All right. So now we've looked at how we can sort of group or pull things in from leading or preceding and following. Now we're going to look at how do we just say, give me something from the next row or give me something from the previous row. And that's a way to use leg and lead. And it allows you to reference a value in a row before or a row after the current row. And you have to use the over clause for the window functioning with this in order to specify the partitioning and the ordering so that it knows what to apply that leg and lead to. All right, so let's jump into that. So here we'll take a look at our table again. Same data we've been looking at all along. But I'm going to say, give me the department year in revenue, and then give me revenue for the previous year as last year revenue from revenue ordered by department ID. So when I run that, you can see here the last year, and again, we could use is null to straighten this out, but the revenue was specified as 10,300, but there is no previous, or 10,030, but there is no previous year, so it comes up as null. Here it's saying, give me 20,000, and the last year revenue is 40,000, which doesn't look quite right because we've ordered by the year, but we haven't included the partitioning here. Wait, yeah. And I'm going to throw that in down here too. And then we're going to order by, again, this is one I threw in kind of at the last minute. I didn't have a chance to test it. So let's run this one again, and we can now see that last year's revenue, these two match, these match, these match, and you'll notice that there's kind of, this one is always the last year's revenue. So it's a way, if you wanted to calculate the difference or the delta between this year's revenue and last year's revenue, are we doing better or are we doing worse than last year, you could do that using the leg function. And again, this here, it's the same query. I only changed leg over to lead to say, give me, oops, what did I do? Give me the next year's. So here, the 20,000 is coming from the following year. The 40,000 is coming from the following year.
That null down there.
Because the department ID changed from 1 to 2, there is no next row in the current partitioning area, partitioning group.
That should have been like 8, right?
Pardon?
No, sorry.
So in the query, let me bring the query back up here.
No, I think I see it.
We've partitioned by department ID. So the windowing function is only looking at these rows here that are highlighted. It's not, as far as the calculation for these, it's not looking at any of these down here because these are in a different department.
Okay.
And here you can see you can use both lead and leg in the same query. No surprise there because the windowing function, and again, I should have used the partitioning by there like I did in the previous ones. So lead and leg give you just a way of looking at the next or the previous row. A little bit easier than using the rows preceding or following.
Are those available in SQL Server 2008?
No. No, those were introduced in 2012. Oh yeah. Yeah. The question was, are those available in 2008 or 2008 R2 effectively? No, they're not. They're only available in 2012 and beyond. And again, all of these partitioning functions that we're looking at from here on out in the presentation today are only in 2012 and beyond. So here we've got the first value and last value, which are new things that have been introduced as well. And you use the over clause to set ranges. And The interesting thing is that last value specifies the last value so far, unless you specify otherwise. So when you're looking at a partition, I would have guessed that last value meant the very last thing in that partition, but not true. It's as it's aggregating through each row, it's the last value you've encountered so far. And we'll take a look at how to change that, how to look at that. So here we're going to select the department ID, revenue, and year. We're going to look at the first value of year, partitioning by department ID, ordering by year. So based off of the data we put in there, I think that first value should be like 1998 or something like that. The last value of the year, I think, was 2012. And here we're going to partition and order by year. But let's take a look at the results we get. So we've got the year, 1998. The first year comes back as 1998. And it remains 1998 for the entire data set, and in fact, or for the entire partition, and it's still 1998 for the next partition, because it just happened to have the same number there. However, the final year so far, which I called it, is looking at the last value, and we're looking at 1998, 99, 2000, so that just keeps incrementing as we go through. It just happens to be the current value in this case, but if the result set was being ordered differently, it would only be the maximum year we've encountered so far. But what if we want to look at the real last value for our entire partition? Not just the last value so far. Well, here we're going to use, let me just show both these together. Here we just said partition by department ID, ordered by year. Again, we're doing partition by department ID, ordered by year, and we're specifying all of the rows unbounded before and after, preceding and following, for the current partition. And here we're doing the same thing, all of those before and all of those after for the current partition. So when we run this, the first value we get is the same as before, and the last value now comes back as the real last value in that partition, not just the last value so far like we ran into a moment ago. Could be very useful if you're doing calculations over a specific date range, where you're trying to do an average or something and you don't know ahead of time how big that date range is. Next, on to percent rank. So it's basically the definition of the number of values that are the same or less than the current value divided by one less than the number of values. I know I don't like to read directly from slides, but I want to keep that in mind. It's the number of values that are the same or less than the current. So same or less than kind of implies it includes ties, and divided by one less than the number of values. So meaning if you've got 10 values and you've got 5 in there somewhere, it just figures out what percentile or what percent rank through that entire scope it's going to come at. Percentile is different. We'll look at percentile in a bit. Percentile tells you where you fall amongst all of the values. Percent rank tells you what percentage of the way through the scores are. So like, let's say you were taking a test and you scored 58 out of 60. That would be somewhere around the 97th percentile. Well, no, that would depend on how many people scored there. But the percent rank would put you around 97% of the rank of the numbers there. Again, I'm having a hard time explaining this one, but let's just take a look at this slide here. So if we're looking at the percent rank by revenue, oops, these two revenues are the worst year, and their percent rank is 0. There is nothing worse than those. These two here, or no, this one here is the next worst rank, and 14% of the values, 14.2% of the values are less than or equal to this one. 21% are less than or equal to this next one. So when we hit the 30,000 here, even though 30,000 is not half of 90,000, which is where we end up our set down here, half of the sales years are worse than 30,000, 50% are worse, and 50% are greater. So in that point, you'd figure out, well, there's your median, that 30,000. So let's take a look at T-SQL and see how that works. So the result set we just looked at, here's the query to run it. We're just going to rank ordered by revenue. And we're not going to use partitioning in this case because we're using the where clause here to filter for only one department. But you could throw partitioning in here if you wanted to get a similar thing out of it. The percent rank ordered by revenue. So you can see when we run this, we get the same results, or oh, it's slightly different here because I had that extra year for 2005 that had been inserted somewhere along the way, I believe. But you can see here that if we look at this 50,000, you can see that 80% or 79%, or yeah, 80% of the years were worse or equal to this one. So it's just a way of figuring out how things rank there. Next, we've got percentile, and two flavors of percentile here, a discrete and a continuous. The continuous, when it's calculating the percentile, it interpolates the appropriate value, where the discrete, it picks a percentile that exists in the exact set. So you might have duplicates, or you might have big wide gaps, and you might say that certain things are at the 80th percentile and there's nothing in the 70th percentile range because of data that's missing, and then you're suddenly at the 60th percentile. Well, continuous would level them out across those open gaps effectively. Keep in mind that any nulls are ignored, and well, percentile cont stands for continuous, percentile disc stands for discrete. And let's just jump in and see how that works. And again, a couple of blog posts here that talk about this in more detail. Department revenue in year. We're going to look at we're trying to establish the 90th percentile, or 0.9. And this is new, within group. We haven't looked at that before. So it's within the group, ordered by revenue, over partitioned by department ID. So the group is implying whatever it's partitioned by. And so this is going to figure out percentile continuous by revenue, broken out by department ID. So let's take a quick look at that.
That's like a group by within the window or something? The within group?
It's the percentile within this here. So it's a way to say order the group by revenue. So you have to know what to do a percentile. Like if I said, give me a percentile of all the people in the room here, we wouldn't know what to do. But if I said, give me a percentile of all the people in the room by age, you could do that. Or by height, you could do that. But, and that's what this order by here is effectively doing, is it's that by age or by height. It's what you're ordering in. So it's showing that for this entire partition, which is department ID, which is department ID of 1, for this entire data set of revenue here, give me the 90th percentile. So if you work through all of these, the 90th percentile is 75,000 based off of that entire set of data there. So if there was some way of grading and saying that anyone that was above the 90th percentile passed and everyone that was below the 90th percentile failed, you could use this to do the calculation and say at any year less than 75,000 in that calculation would be a fail. Every year above 75,000 is a pass. But what you'll notice is that although the percentile here is 75,000, there is no 75,000 in this list here. It's doing percentile continuous, meaning it's assuming you've got the entire range to work with. Now, if we take that exact same query and we just change the percentile continuous to percentile discrete and run it, notice the percentile discrete is now 80,000 because it goes down here and says, okay, 75,000 kind of falls in between one of these, so we've got to pick one of these, and I guess it's rounding up in this case and taking 80,000 because it's the only thing that's above that 90th percentile. So if we wanted to change it and look at like the 50th percentile, if we didn't have as high of grading standards as we might have in this theoretical class. You can see that the 50th percentile is 20,000. So anything that's below $20,000 in this list is in the bottom 50% of all revenue years. And here I've got 50% with looking at percentile, discrete, and continuous. And when we run those, 50% is effectively the median. So we're giving the median discrete is at 20,000. The median continuous is at 25,000. We're able to get 25,000 on the continuous because it falls somewhere in between these two right here, so you can see one of them is a little bit more accurate on precision, but the other one will give you an actual value that exists in your data set. All right, how are we doing on time? Okay, cumulative distribution. Take a look at how things map in a bell curve, for instance. It maps all of the values to their percentile rank in a distribution. So rather than just reading the slides, let's just jump into the sample here. So we're looking at the same data again, cumulative distribution over ordering by year where the department ID equals 1. So we're only looking at a single department ID here. And you can see that the cumulative distribution, it's saying that this is 6% of the way through the entire data set. This is 100%. This is the top score. This one is 75% of the way through the entire data set. So where previously we were looking at the percentile that gave us what is the number that is at a specific percentile, this is giving us what percentage of the way through the entire set are we. So that's cumulative distribution. That was ordering by years. Now I'm changing it to order by revenue. So here, these three are the same, are the worst revenue year, and they're all tied here for the cumulative distribution. So then there's a few more ties down here where they're all the same. So you can see that depending on what you put in the over, that cumulative distribution gives you a different value there. Let's see. So here, this is the one we just ran, the order by revenue. Here we're going to look at the cumulative distribution, ordering by revenue, same thing we just looked at, and we're going to round it. No, first we're going to multiply it by 100 and round it off to a solid number, and that will give us the percent less than or equal the current row. So here the 0.1875 rounds out to 18.8 with one decimal. And so 18.8% of the values in the entire set are less than or equal to 10,000. All right, so I think so far a lot of this cumulative distribution, percentile, percent rank, and all that's a bit dry. So let's make it a little bit interesting. And we want to look at some random functions and testing probability of dice rolls. So random number generators on computers, are they ever really entirely random? No, because they're being created programmatically somehow. Okay, so let's take a look at here. So I'm going to create a table called random numbers that has one column in it that's just called rnum, which is an integer. From a previous example I was deleting from it, that doesn't matter. Then I'm going to declare max and min of 101, and I'm going to insert, I'm just doing math here to take random and figure out how to insert values between 0 and 100, and I'm going to use the go statement to execute this chunk of code 10,000 times. So I'm going to create the table, insert 10,000 rows to it, sit here and twiddle our thumbs for a little bit. There we go, we're done. Then what I'm going to look at is I'm going to select distinct random number, or distinct of the whole thing, and I'm looking at the number, and then the cumulative distribution ordered by the number times 100. So we're basically bringing out a percentage here to figure out what percentage. So if I look here, the random number is 1, and 1.03% of all of those 10,000 rows is less than or equal to 1. 2.11% is less than or equal to 2. Well, it's not entirely random, as you can see. based off that cumulative distribution. But if we go one step further and push that into a subquery, we grab the cumulative distribution, we use the lag function to look at the previous row, ordered by the number, and subtract the current row from the previous row. That's going to give us the percentage of that number turning up randomly. Or it's going to give us the difference, what am I saying? The difference between the last and the previous. But, as was pointed out earlier, we run into problems with null. Let's go fix that and throw an is null in here around our calculation. And now we can see that 1.03% of the random numbers of 1 through 100 went in the category 1. As we scroll down here, 0.84, so the number 22 only comes up 0.84% of the time in this specific case. So if you were using this random number generator in some type of a gambling way, it might not be particularly fair.
Put your card on 22.
In that case, 22 is a really good one. Yeah.
Powerball's pretty good.
Or a bad one, depending on how you're looking at it, whether you want to hit your number or not. All right, so what are the odds that T-SQL random number generator will generate a given number between 1 and 100? Or between 0 and 100? It's about 1%. However, we just showed that that's not entirely accurate. Now, if we'd gone up here and maybe inserted 100,000 or 1,000,000 in that table, it might end up being closer. If we'd only inserted 100, it would probably be even further off. So, next, when we're rolling dice, are the odds of rolling a 7 the same as the odds of rolling an 8, or sorry, a 9 or a 2 or an 11?
Depends how many dice you roll.
Okay, good result. Good. It depends on how many dice we roll. Okay, a typical double, 2 dice that are 6-sided dice, like you're playing Monopoly. Are the odds the same? No. Okay. Now, are the odds of getting specific numbers when rolling dice different than a random number generator generating numbers between 2 and 12? The answer is yes. Now, the reason is because to roll a 2, you have to roll 2 ones. But to roll a 7, you could roll a 6 and a 1, a 5 and a 2, a 3 and a 4, and a number of other combinations that you can figure out there real quick. So there's more ways to roll a 7 than there are to roll a 2. So I think if you're playing craps, 7 is a bad thing that happens. I don't know, anybody know?
This is the opposite.
Yeah. Okay. So what we're going to do here is we're going to create a table called dice rolls. And let's just pretend you're creating a video game to do something with dice. In this case, if you had a random number generator to generate numbers between 2 and 12, it might not be the same as rolling real dice. So we're going to come up with a table that holds the first die and the second die. It's empty, but we're going to delete from it anyway. We're then going to roll 2 random numbers between 1 and 6 inclusive, and it's going to do that 1,000 times into that table. Okay, so it did it. We got 1,000 rows inserted there. We're going to select out of that table, just take a look at it, and that simulates one of us sitting here 1,000 times and rolling Monopoly dice or whatever it may be. Then what I want to look at is the first die plus the second die total, which gives us our total roll. So here's 6, 8, 11, 5, whatever the numbers are that were rolled there. And then I want to look at the cumulative distribution of that, ordered by the total roll, selecting the total from that subquery there. So here, let's see. We can see there's the cumulative distribution, but let's do some cleanup on it with some is null and some rounding and multiplying by 100, and so we can actually get a percentage value out of it. So there you can see that 3.6 of the time in this data set, a 2 was rolled. 2.4% of the time, a 12 was rolled. But 2 and 12 should be about the same odds of being rolled, where 15% of the time, a 7 was rolled. So if you're going to bet on these numbers, I'd rather bet on a 7 than on a 2 or a 12. Okay, so now I'm going to delete from dice rolls, and I'm going to put in 10,000 instead of just 1,000 items. This will take a little bit longer, but hopefully it'll give us a little bit more statistically significant data because our data set is a little bit larger and we've got more random numbers to work with. Same query we ran a moment ago, looking at the current one, the previous one, ordered by the total roll and all that. And here we can see 2.7 and 2.9 on 2 and 12. They're about the same. They're closer than they were before. And the way it works is 3s and 11s should be about the same. 4s and 10s should be about the same, and they are about the same. And you can see going through there, they're more statistically significant at this point. How about if we do the same thing with 1,000,000 rows? All right, we don't have time for that. But you can imagine what would happen if you want, just uncomment, download the code, uncomment this chunk here, run it yourself, let it go overnight, whatever it takes. But effectively, you're going to end up coming out with a little bit more accurate odds there based off of a larger set of data. On to the quiz.
So what about that order by new ID trick for getting a random order?
That's a really good question. So the question was, what about the order by, or using new ID to generate random numbers? And I do this a lot of the time. I really don't like GUIDs in the database or unique identifiers, but I love them for generating random numbers. Where you take it and you cast it as like a var binary and then you do a mod on it or something to figure out from a GUID what your random number is. It would be interesting, and I can do this afterwards here, to replace the typical random function with that method of doing it and see if you really get the same randomness out of it. Yeah, that's a great question. All right. Oh, this is your part of the quiz first, Aaron?
All right. Hopefully you remember back to the beginning. First question is, which of the following is incorrect? In regards to top n%, n can be any value. N can be any value from 0 to 100. N can be a variable valued 0 to 100. So which one I think is incorrect? You think first one is incorrect?
What makes that one difficult is it's one of those backwards questions where it's not asking what's correct, it's what's incorrect.
Yeah. All right. So the next question is, if a table with 4 values of I and another value with 2 in column A, what will the result?
Ones and twos.
Ones and twos. What will be the result set with the following statement? Select dense rank over order by column A, ascending, as column A, from test table. Which picture will represent the result set? A result set where all the rows except for the last one is 5. A result set where the row numbers match the values.
C.
See, meaning the rightmost one.
Yeah. Yeah, I should have labeled those. Yep, the one on the right is correct. Okay, this one's a little bit more wordy. So if a duplicate value is encountered, row number does which of the following? Repeat the row counter number until the first non-dupe is found, and then continue with the next row number. Continue to increase the counter row number when a duplicate is found, or repeat the row counter number until the first non-dupe is found, and then skip to the next number, which would match the row number as if no dupes were encountered.
B.
B?
Yeah, if we had letters.
Yeah. Again,
The middle one.
there's 2 tests here, a test for communication and figuring out the right SQL answer.
C.
Yeah. All right, good job. On to Steve's question.
All right, so the Ntile function. If we're using an Ntile with a parameter of 100, this is also known as what?
Percentile.
And there's the example, percentile. So it's breaking it up into 100 bins, and it's sorting the entire result set out over those 100. All right. So the query fragment above uses up to how many rows in the average calculation?
3.
Okay, everyone's agreeing 3 rows? Yay! So because it's using the current row and the 2 before it. And that one threw me off a couple times when I was creating the demos. All right, so here we're at. Any questions at this point over any of the stuff we've covered? I'm going to flip over to Google Hangouts and see, turn on. Oh, I don't know how to turn on questions. Whoever's viewing, apologies, I don't know how to turn on questions, but you can email me questions if you're viewing it remotely, if you want, or hit me with the questions on Google Plus, where we'll be broadcasting this through. So, anybody in the room have any questions on anything we've covered here today?
I have any other question.
Okay, we'll get to that in a second. So, for more information, visit emergency reporting to find out about, or emergencyreporting.com to find out about what emergency reporting is. Aaron is on the web at aaronbooma.com, and on Twitter is AaronDBooma, and I'm on the web at stevestedman.com, and on Twitter as SQLEMT. Tune in next week, same bat time, same bat channel, as they say. The 12th at 9 o'clock a.m. Pacific time. We're going to cover set operators, union all, intersect, except, and some set grouping.
Logic.
Thanks everyone for coming. We'll stop the broadcast.